Now in Chapter 10, we go back to examine our calculus in more detail and see how we can use it to help primarily to understand the graph of a particular function. So we use the calculus, the first derivative, and later in the chapter you'll see we also look at second derivative of a function so that we can build a picture of what the graph would look like. There's some interesting points on graphs. They are what we call turning points, maximums, minimums, etc. Points of discontinuity. Yes, and they will be the features that we will focus on throughout this chapter. So, to get started, let's go back to looking at little imaginary tangents drawn along a curve and thinking about the gradient of those tangents. So you can see here that we've got a function and obviously we've got some little plus signs here indicating if we drew a tangent it would have a positive gradient. At this very top turning point, if we drew the tangent it has a 0 gradient. Now in this next section you can see negatives. Again at the bottom the gradient is 0 and then positives thereafter. Some features of the graph. So we could see that the first derivative should be a positive number, first derivative should be 0, first derivative should be a negative, first derivative should be a positive number again. So what sort of physical features of a graph are represented by these positives, zeros and negatives? So what you actually learn is that if the first derivative is a positive, your function graph is actually increasing. So when I talk about the function, I really mean the y values of the function. So the function or its y values are increasing in these two sections. The graph, if you like, is going up. The graph is going up. And in the negative section, the graph is obviously coming down. And then at the 0 points, where the derivative is 0, we say our function is stationary. And a stationary point often creates a turning point. So we've got that a curve is increasing. If a curve is increasing, f dash x will be greater than 0. Greater than 0 means positive. The first derivative should be a positive number. We can see that they change in size of the positiveness. So here you can see it has a positive gradient, but as you get closer and closer it's less positive. Still positive, but only very slightly positive until it actually gets to 0. If a curve is decreasing, the first derivative is less than 0, or the first derivative is a negative number, which we can see on the graph. And if a curve is stationary, that is at a turning point, then the first derivative is actually equal to 0. These conditions are really important that you learn these off by heart. To help you learn them, I'd suggest that at the beginning of every question that's asking you about an increasing, a decreasing or a stationary point or points, that you actually start with this statement. A curve is increasing if f dash x is greater than 0, etc. You can see here in these examples, I've done exactly that. So this first question said find all values of x. So that says we'll be solving for x, for which the curve is decreasing. We should start off immediately. A curve is decreasing if, and you state your mathematical fact or property. We don't do any maths unless it's based on a mathematical fact, property, rule, etc. So we need to learn this. It's a rule that you have to know and state it in your solution. So we've established that the first derivative has to be less than naught. Let's find the first derivative. The first derivative would be 4x minus 1, and we want to know where 4x minus 1 is less than naught. That's a nice linear inequality. To solve a linear equality, we just treat it like a linear equation, unless of course you're multiplying or dividing by a negative, which we're not here, and so you get the solution x is less than a quarter. So at all points on the graph where x is less than a quarter, the graph is coming down. We have a graphical representation of that. We know that this function, 2x squared minus x, is a parabola. If I factorise the right-hand side, you can see, and put it equal to 0 to find where this function actually cuts the x-axis, you can see it cuts at naught, and when 2x minus 1 is naught, so x is half. So it actually looks like this, and yes, you can see that this function was decreasing all the way to there. What x values produce that part of the graph? It was these, where x is less than a quarter. Next example, it asks you to show that the function is always decreasing again. So state what it would mean or how we would know when a curve is decreasing. A curve is decreasing if the first derivative is less than naught. So we find the first derivative. F dash x in this case is negative 2. Negative 2 is less than naught. So the derivative or the gradient never changes. And we know that. This graph, this function's not difficult to sketch. It's a straight line with a negative gradient cutting at negative 7. And yeah, for sure, that graph is always decreasing. The next examples ask you to find x values. We'll be solving something for which this function is stationary. What do we know about that? A curve is stationary if the first derivative is actually equal to naught. Find your first derivative and solve it equal to naught. Question 4, or example 4, wants where this function has no stationary points. And so a curve has no stationary points if what? If the gradient never equals 0. Therefore, we'll be showing that the gradient is never 0. You'll need to rewrite that in the format f of x is equal to x to the half. Find an expression for the derivative, a half x to the minus a half, which is 1 over 2 square root of x, and x can never equal 0 as it is in the denominator. So what have we shown, or what can we see? We can see that the first derivative can never be 0. If the first derivative can never be 0, there are no stationary points.